I hope all of you are doing well.
Today we are going to discuss a very interesting and important topic: how satellite imagery, artificial intelligence and GIS technology are transforming biomass residue assessment and agricultural intelligence. Now, whenever we hear the word crop residue, most people think of agricultural waste left behind after harvesting. But what if I told you that this is called waste actually hold huge value? What if farmers, industries and government could use this data to create cleaner energy, better planning and smarter agricultural system? The real challenge is not availability. The real challenge is accurate assessment. Because when biomass estimation is slow or inaccurate, industries struggle with supply planning, policymakers face decision-making issues, and farmers lose potential opportunities. And that's where technology changes everything. Today with the help of AI, satellite imagery and geospatial analytics, we can estimate biomass availability faster and more accurately than even before. So, through this presentation, let's explore how modern technology is transforming biomass assessment from a manual process into an intelligent data-driven system. So, before moving into the technical part, let me first introduce our organization and what exactly we do. Planeteye Farm-AI work in the field of AI-powered geospatial intelligence for agriculture and biomass analytics. In simple words, we use modern technology like satellite, artificial intelligence, GIS mapping, and data analytics to generate agricultural insight. Now that you have a basic understand about Planeteye Farm-AI and technology we use, before moving further, I would like to show you a short video. This video will give a simple overview of what biomass actually is, why agricultural residue is important, and how biomass is becoming a valuable resource for renewable energy and sustainable industry. This video will help everyone quickly connect the concept before we move into the technical and analytical part of the presentation. So let's watch this short introduction video on biomass. I hope the video gave everyone a clear basic understanding of biomass and its real world importance. As we saw, agriculture residue is no longer considered waste. Today, it is becoming an important resource for bioenergy, biofuels, biomass power generation, and sustainable industrial application. Now, the important question is, how do we accurately identify and estimate biomass availability across a large geographical areas? And that is exactly where satellite imagery, AI, and geospatial analytics play a major role. So now let's move ahead and understand traditional challenges in traditional biomass surveys. Traditionally, biomass assessment has been carried out through manual field surveys and ground level inspection. Farmer survey team and field officer collect crop residues information physically from different locations. Also, this approach provides basic information. It becomes difficult when assessments are required across large village, talukas and district level. Traditional surveys are often time consuming and labor intensive and expensive to conduct regularly. And another major challenge is limited geographical coverage. Since field teams cannot visit every farm frequently, the collected data may not fully represent the actual biomass availability across the region. Data inconsistency is also a common issue because survey results may vary depending on survey method, sampling processes, or human observation. In addition, crop conditions change dynamically due to weather, irrigation, harvesting cycle, and seasonal variation, make it difficult to maintain up-to-date biomass record using conventional method. So, this limitation increase operational cost and slow down decision making for industries, bioenergy projects, and agricultural planning. This is why there is a growing need for AI-driven, satellite-based, and geospatial biomass intelligence system that can provide faster, scalable, and more accurate assessment in real time. So, in this slide, we discuss about why it is important. So, biomass residue assessment plays an important role in agriculture, renewable energy, and sustainable resource management. Crop residue such as wheat straw, sugarcane trash, rice straw, and cotton stalk can become valuable biomass resource when properly assessed and managed. One of the major benefits of biomass assessment is in ensuring a reliable biomass supply. Accurate estimation help industries and bioenergy plant understand how much biomass is available in a particular region and whether the supply can support long-term operation. It is also very important for bioenergy and CBG project. Biomass availability data help identify suitable location for biomass, biogas plant, biofuel production, and other renewable energy initiatives. Another key advantage is better supply chain planning. With proper biomass mapping and geospatial analytics, organization can optimize transportation, storage, and collection process, reducing operational challenges and cost. Biomass residue assessment also support sustainability and carbon reduction goals. Instead of burning crop residue in field, the biomass can be utilized for clean energy generation and industrial application, helping reduce environmental pollution and carbon emission. Overall, biomass intelligence helps create a more sustainable agriculture ecosystem while supporting energy security, efficient resource utilization, and climate-friendly development. Now, let's look at the modern biomass assessment approach powered by satellite data, AI, and GIS technology. This integrated framework allows us to assess biomass availability much faster and more accurate compared to traditional survey methods. Satellite imagery help continuous monitoring crop growth and agricultural patterns over large area. Artificial intelligence process this data to identify crop type, estimate production, and calculate biomass residue potential. GIS and Geo-Spatial analytics further help in creating biomass distribution map, heat map, and location-based insight for planning and decision making. To ensure reliability, the satellite-based output are also validated using ground survey observation. Overall, this modern technology framework enables scalable, data-driven, and real-time biomass intelligence for agricultural and renewable energy application. So, on this side, we are highlighting what we do at Planeteye Farm-AI and technologies we use to deliver agricultural intelligence solution. Our work is mainly driven by satellite imagery and geospatial analytics. These technologies help us monitoring agricultural at large scale with better speed, accuracy, and efficiency. Using this integrated approach, we provide several core solutions such as crop mapping and classification, biomass residue assessment, and soil and water analytics, and AI-based geospatial solution. Satellite data help us observe crop condition and land use pattern, while AI models process the data to generate meaningful agricultural insight. GIS and geospatial analytics further help in creating map, heat map, and decision support system for planning and monitoring. Overall, our goal is to deliver accurate, scalable, and data-driven agricultural intelligence, support farmers, industries, and sustainable resources. Before moving deeper into case study, let us quickly understand complete workflow of modern biomass intelligent generation. The workflow starts with satellite image acquisition. Satellite system continuously capture multi-seasonal agricultural data. After data collection, image processing is performed. This includes cloud removal, geometric correction, radiometric correction, data enhancement. The next step is AI-based crop classification. Artificial intelligence identifies crop pattern using spectral and temporal signature. After crop identification, GIS analytics are applied. This helps generate crop distribution map, biomass hotspot map, zone-wise intelligence, and transportation analysis. Then the crop area and yield model estimate production and residue generation. Finally, field validation is performed for quality improvement. So this workflow creates a complete biomass intelligent framework. The major benefit of this system is that entire process becomes scalable, faster and highly data driven. Now, till this point we understood why biomass assessment is important, what challenges exist in traditional method, and how modern technology are improving the process. So, now to explain the practical implementation and part in more detail, I would like to hand over the session to Ruturaj sir. Sir will now take you through the real case study and explain how satellite imagery, AI and GIS were actually used for village level or district or large level biomass assessment and analytics. Over to you, sir.
Good morning everyone and welcome to today's webinar. First, Rutuja ma'am explained all of concept of the biomass and related all the problems and now also on. And then I am explain the case study of the related to the biomass estimation. First of the case study is introduced Keria Ranpur village. Now let's move to the real world case study conducted in Keria Ranpur village located in Gujarat. The objective of this case study was demonstrate how satellite imagery, artificial intelligence and GIS remote sensing technology can be integrated to generate accurate biomass intelligence at village level. Traditional biomass assessment depends on manual survey and field visits, which are often slow, expensive and difficult. So scale through the project we aim to create a faster, scalable and data-driven approach for crop mapping and biomass estimation. The study area include multiple seasonal crops such as cotton, wheat, mustard, maize and castor. These crops generate significant agricultural residue that can be utilized for bioenergy, industrial processing and sustainable biomass supply chain. Using the satellite data and geospatial analytics, we perform crop classification, cultivated area estimation, yield predictions, biomass residues assessments and village level biomass mapping. This case study highlights how modern geospatial technology can support renewable energy projects, biomass procurement, planning, sustainable agriculture and climate smart resource management. Uh, in this phase, satellite imagery and AI-based classification model were used to identify crops at the field level. Different crops have the unique seasonal spectral signature, vegetation patterns, and growth cycles. Using these characteristics, we classify major crops including cotton, wheat, mustard, maize, and castor. This classification process involves satellite imagery, pre-processing vegetation in the index analysis, temporal monitoring, and AI-driven geospatial analytics. One of the biggest advantage of the satellite-based crop classification is speed and scalability. The large agriculture region can be analyzed in a very short time compared to the traditional field survey. The approach also improves consistency and reduce dependency on manual data collection. Accurate crop classification is extremely important because it's the foundation for the production estimation and biomass residue calculation. These types of technology enable governments, industries and agribusiness to generate a real-time agriculture intelligence for planning and decision making. Now, crop area, yield and production estimation. After crop classification, the next step was a crop area, yield and production estimation. Using satellites, satellite analytics, seasonal crop monitoring and AI-based crop models, we estimate cultivated area, predicted crop productivity for each crop categories. The analysis included total cultivated area, are mapping, crop-wise yield estimation, production forecasting, seasonal agriculture monitoring. This information is extremely important because biomass residue generation directly depends on crop production level. Higher crop production generally result in higher biomass availability. This as analysis combines remote sensing data, vegetation health indicators, geospatial analytics, and crop growth models to generate reliable agriculture intelligence. These outputs helps to industry and renewable energy projects estimate bioavailability for supply chain planning and long-term operational and strategies. Now next is the harvest and residue generation timeline. One of the most important component of the biomass intelligence is understand harvesting schedules and residue generation timeline. Different crop generate biomass residue at a different time of the year. Therefore, seasonal crop monitoring because essential for biomass collection, planning, and industrial utilization. Using satellite monitoring and crop calendar analytics, we identify the harvesting period and residue availability windows for major crops in the study area. For example, wheat residue is mainly available during the March and April. Cotton residue is become available between October and January. Mustard and maize residue is follows a separate seasonal and cycle. This so on. This information is extremely useful for industrials involved in biomass procurement, bioenergy production, and supply chain operation. Accurate residue timeline help to optimize biomass collection, scheduling, transportation planning, storage management, procurement operation, industrial feed, stock supply, connectivity. Overall, the seasonal biomass intelligence improve the operational efficiency and reduce the supply chain uncertainty. Now, calculation for crop area, yield and biomass estimation. On this, we are showing the crop production and biomass assessment workflow conducted for Keria, Ranpur village. Using the satellite image, GIS analytics and AI-based crop models, we estimate crop area, crop production and biomass residue generation at the village level. This workflow combines geospatial analytics, crop modeling and biomass estimation methodologies to generate the actionable agriculture intelligence. And where wheat is taken as an example for the biomass residue estimation, to estimate the biomass generation, we apply crop residue ratios commonly known as a CRR value. This ratio helps to estimate the quality of the crop residue generated after harvesting. For wheat stock ratio conducted was 1.5 and wheat husk ratio is considered was 0.3. Based on production analysis, the estimated wheat stock biomass generated in the village was approximately 17,396.8 quintals. The dashboard visualization on the right demonstrate how satellite imagery, biomass density mapping, AI-based analytics and geospatial intelligence are integrated to generate the field-level biomass insight. These types of analysis supports the biomass supply chain planning, biofuel and bioenergy projects, crop residue management, procurement operations, sustainable agriculture planning. Overall, this demonstrates how AI and remote sensing technology can transform agriculture monitoring into the intelligence, scalable and data-driven biomass assessment systems. Now the village level biomass intelligence. This slide demonstrate the village level biomass intelligence generate using the integrate the satellite analytics and GIS-based spatial mapping. The system provide crop-wise biomass estimation, level of biomass mapping, seasonal biomass trend, and biomass hotspot identify across the study region. We identify the major biomass categories including wheat straw, cotton straw, mustard residues, and maize residues. Using geospatial technology and intelligence, biomass availability can be visualize spatial across different farms and agriculture zone. This helps the industry and governments agencies identify high biomass connection area and optimize the resource planning. Village level biomass intelligence also support biomass aggregation planning, renewable energy and feasibility studies, transportation optimization, storage infrastructure planning, sustainable biomass scoring and strategies. Such geospatial analytics create a strong foundation for the efficient biomass management and climate smart agriculture development. Now next is a key challenge and validation of the framework. All through the satellite based biomass assessment provide major advantages. Certain technical and operational challenges still exists. One major challenge is mixed cropping patterns, especially in a small farms. When multiple crops are growing together, crop classification accuracy can be affected. Seasonal variability, atmospheric condition, and cloud cover can also influence the satellite data and availability. Another important factor is a field level validation, ground truth survey, and residue to producer ratio verification are necessary to improve the reliability and accuracy of the biomass estimation. Therefore, the hybrid framework of combined satellite analytics, GIS mapping, AI model, ground surveys, field validation create a more and accurate biomass intelligence system. This integrated approach improves the confidence in biomass estimation and support the industrial scale and decision making. Now the very important future of the biomass intelligence. The future of the biomass intelligence is rapidly evolving with the continuous advancement in artificial intelligence, remote sensing, and geospatial technology. Real-time satellites monitoring system will be enabled to continuous crop and biomass tracking across the multiple season and large scale of the region. Advanced AI models and deep learning algorithms will automate crop classification, biomass estimation, and yield prediction with much higher accuracy and efficiency. The integrations of the high resolutions satellite imagery and drone based monitoring system will be further improve field level analytics and precision agriculture capability. Future of the biomass intelligence platform will be include first is the predictive analytics, biomass forecasting models, real-time dashboard, automates reporting system, smart supply chain. Overall, the future of the biomass intelligence lies in the fully digital, AI-powered and real-time geospatial ecosystem. This is the case study and all of the solution of the case study. Now next is explain also again in Rutuja ma'am.
Thank you so much, sir, for explaining the case study in such a detailed and insightful way. I hope everyone got a clear understanding how this technology are practically used in real world scenarios. Now, so now let us summarize the key takeaways from today's webinar. The first key takeaway is the satellite and AI technology enables faster biomass assessment. Large-scale crop and residue analysis can now be performed rapidly and efficiently. The second takeaway is that GIS improves spatial intelligence. Village level, level, and industry level mapping support better decision making. And the third takeaway is that hybrid approach improve accuracy. Combining satellite analytics with ground validation create more reliable system. And the fourth takeaway is that biomass intelligence supports sustainable energy. Geospatial analytics help industries optimize biomass sourcing, logistics, and supply chain planning. Today, biomass intelligence is becoming essential for renewable energy planning, ESG initiatives, sustainable agriculture, carbon reduction strategies, bioenergy supply chain. The future of agriculture and biomass analytics is a digital, data-driven, and geospatial. Organizations that adopt this technology early will gain significant operational and strategic advantages. At Planeteye Farm-AI, we are committed to build scalable agriculture intelligence system using satellite imagery, AI, GIS, and geospatial analytics. So, thank you everyone for joining today's webinar.